Okay. So this is one very interesting problem. One of the first problems that I was solving when I had just joined as a master's student at IIT Madras. Uh, it's a very common problem. That is, if you have any analog circuit, be it current mirrors, oscillators, or even amplifiers, single-ended amplifiers, the noise of the bias circuitry would usually impact the noise of the circuit. So what we do is that to either filter the noise or to reduce the noise, the classic approach is to just use filters. So a simplest filter is an RC filter shown here, okay? And ideally, if you want to kill the bias noise. So for example, the bias noise can be something like, if I have a circuit, let me show an example. Yeah. Yeah. The bias noise can be something like a current source. So if you see here, this circuit, you have a current source I0 here, and this current is mirrored by a factor N in the circuit. Okay, I'm mirroring by a factor N in the circuit. And the noise of the current source, so usually when I'm drawing as a current source, there will be some reference circuit which will generate this current. So we are going to call that as, okay. Yeah, so we are going to call that as some reference block. And the noise of that current source and also the noise of all these mirroring transistors will all get amplified by the mirroring ratio 1:n here, right? So this is just a 1:1 current mirror. So if I'm injecting a current I0 here, I'll get the same current I0 here as well. And at the output, I'm going to get N times I0. Okay. So this current may be going as a biasing current for some circuit. So I'm interested in minimizing the noise of the biasing current. One classic way of doing that is just put a filter, RC filter. Okay, we'll go deeper into why should we choose this capacitor with respect to the ground and supply and all that at a later stage. All I'm trying to tell you is that you have some noise source and you want to filter it out. And to filter it out, you're using an RC circuit, which is shown. Okay, so you're using an RC circuit to filter out the noise. You can also filter. In my application, I was trying to filter out spurs. So I'll come to the problem. The problem is that usually you can put filters with very low cutoffs. Okay. The problem is that you will literally kill all the high frequency noise, right? So if you put a low pass filter, has a frequency characteristics that looks something like this. So I'll kill all the noise after 1/2 pi RC. So I'm able to filter out all the noise after that. So if let's say you're concerned about noise at some specific frequency, you can choose the pole frequency in such a way so that you get sufficient attenuation. Because that's a classic filter design problem. But in analog circuits, area is the most important thing to keep in mind. You can't just arbitrarily keep putting as large a filter as you want, but area usually restricts how much filter can you have. Yeah. So one of the questions was, can you elaborate a bit on spurs? A spur is nothing but, see, noise is nothing but, if you plot its power spectral density, a noise will look something like this. Its energy will be distributed over a range of frequencies. If I ask you what is the power at any one specific frequency, if I ask you what is the power at some specific frequency fx, it is 0. Okay, so that's why we call it density plots. But spurs are also noise, but those are periodic sources, meaning if you plot its power spectral density, it will have impulses at those frequencies. Okay, and if I ask you what is the power at this frequency f spur, it will be a finite number. So a difference between spur is also a noise and unwanted periodic component in the circuit. Okay, you have some circuit and it's an unwanted periodic component. And let's say you want to remove that unwanted periodic component. Okay, so let me give you an example. Where will you get an unwanted periodic component is, I'll just take a very simple classic single stage amplifier. And let's say on supply, you have a ripple. Okay. You're trying to amplify an input signal. At the output signal, let's say this output signal, let's assume it's a power amplifier. So it's driving a audio amplifier, okay, a speaker. So what you would expect to hear in the speaker is the song that you are trying to amplify. A song can be converted to a voltage signal and it is being amplified by the circuit. That is what your speaker is supposed to speed up. I mean, it's just able to, it's just supposed to give you the song, which is the input signal. But on top of it, you may also hear some kind of ringing noise. Okay. If you have ever been in any classroom where there were speakers, old generation speakers, they will tend to produce this ringing noise. So it's often called feedback. I'll probably talk about that at a later stage. What happens? Yeah, the word that is English word used to describe that is called feedback. A kind of a ringing noise would be heard on top of this song that you're trying to hear. So that ringing noise is because of this ripple. A ripple is like you have your supply voltage, which is ideal supply. On top of it, there is some small sinusoidal signal riding on top of it. Where does the sinusoid come from? So the sources can be varied, but typically what happens is that the supply voltages are generated using a circuits called buck and boost converters. So those circuits are called DC-DC converters. So for example, let me give you an example. If you take your cell phone, you'll have a 3 volt or a 5 volt battery. Okay, let's say you have a 5 volt battery, and I'm just taking an example. The numbers are not important here. Exact numbers are not important, but you have a 5 volt battery and you have an RF chip, a baseband chip. The baseband chip is a DSP, digital signal processing chip, and maybe a microcontroller, which is controlling, or a DSP itself can do all those things. And then there is an RF chip, which transmits your signals into free space. Okay. And each of these chips may be operating at different supplies. So what we do is that we take the 5 volt battery. From the 5 volt battery, we derive, say you need RF circuit, say needs 3 volts. And DSP circuit, say it needs 1 volt. Usually core devices, low voltage devices, so they'll need lower voltages. So I need to derive 3 volts, 1 volt, all from this 5 volt supply. It's a 5 volt DC supply, which is your battery. From that 5 volt DC, you need to generate 3 volt DC, 1 volt DC. So this process is what we call DC-DC conversions. Okay. So AC to DC is what we call rectification, right? So AC to DC is what we normally see in most of our electronic devices. If you see, the power that comes to your house is an AC power. So normally you will have an adapter or the charger, as we call it. Essentially, it's an AC to DC converter. It will receive the AC power and it will convert the sine wave to a nearly a constant signal. So when you convert the sine wave to a constant signal, there are some standard circuits for it. What happens is that your supply will have some ripple. Okay, there will be a DC value. On top of it, there will be an AC component. And the frequency of the AC component will be 60 hertz. I mean, 60 or 50 hertz, depending on which country you're in. That's the frequency of the ripple. Okay, so that's what you will normally see on your supply in an AC-DC conversion. In a DC to DC converter, there are different approach. How do you convert 5 volts to 3 volts? One simple circuit I'll just draw, which most of you guys must have at least seen in any basic course on circuits, is what we call feedback regulators, voltage regulators. So you can, let's say you have a voltage of 5 volts here, and from this you need to derive 3 volts. You can do something like this. You can put an op-amp. So this is an op-amp structure. So since it's an op-amp, I can choose the resistors in such a way, R2 and R1, so that your output voltage be not. So in this case, I think you get an amplification. You can choose. Let me show a simpler structure here. So let's say this is your circuit. which needs a 3 volt output voltage. And you're supposed to derive that 3 volts from a 5 volt supply. So the details as to how, since some of you are just undergraduates, I think some of you are master students, so you'll be able to see and appreciate the circuit immediately. Undergraduates, don't have to worry. So there are these are some very, very simple circuits, and you will learn it in another year or two. But all I'm trying to tell you is that there are different ways of converting a 5 volt. Let's say I take a 5 volt, put a resistor divider, and convert it to 3 volts. Okay, so I can convert it to a 3 volt by doing this. So for example, I think, so this is say 6R, and say I choose 4R. A potential division between resistor 6R and 4R will give me 3 volts. And why do we do this? Why do we put this negative feedback and all that? I'll come to that later. For master students, you will immediately see this structure is a voltage regulator. So this also converts a DC input 5 volts to a DC input of 3 volts. This is also a DC to DC converter. But this class of DC to DC converters are called feedback regulators. Okay, so these are voltage regulators, and they're called feedback regulators. So this is a field in itself. So you'll have dedicated engineers designing these circuits. Okay, and within this RF chip itself, you will have different blocks inside a chip. Inside a cell phone, you will have an RF chip, and within the RF chip, you will have different blocks operating at different supplies. And you need to derive those different supplies using a feedback regulator. The problem with this approach of converting DC to DC is that you end up wasting a lot of power in the amplifier. And even in this device is called pass device. Even here, you end up wasting the power. So one other solution for this is what we call switching regulators, switching DC-DC converters. So I won't go into the details of the circuit implementation of switching. We'll probably talk about it in a later lecture. These are a set of circuits which use inductors and capacitors and some switches. And they also do the same job of converting, say, 5 volts to 3 volts, or it can convert some 5 volts to 1 volt, but with much lower power dissipation, meaning the efficiency of conversion will be much higher in this case. Okay. So for example, if you take your adapters, you're converting sinusoids to DC voltage source. So therefore, there will be some loss in the process. And that we compute the efficiency as the output power delivered to the load divided by the input power drawn from the high voltage supply, whatever the input supply is. Okay. So that is what we call efficiency, and efficiency will be very high for switching regulators. Okay, so this one is very simple. It doesn't involve any inductors and all that. It's extremely simple. You can just put it on a chip, on a CMOS chip, and just fabricate it along with other devices. And in a single device, your solution is complete. But for switching regulators, you may need a separate chip because it has to have inductors and all of it. Sometimes you have switching regulators on a printed circuit board. Okay, you'll have a PCB. Even your cell phone may have an internal PCB. And that internal PCB will contain the switching regulators. So usually for integrating solutions, we prefer feedback-based regulator structures, but they are not that power efficient. So this class of regulators, switching regulators, will use some clock pulse, okay? And the output DC voltage will be proportional to the pulse width. You can think of it like that. So what happens is, all I'm trying to tell you is that by using a switching regulator also, you will produce a desired DC voltage of 3 volts, but you will have some unwanted high frequency components running on top of it. Periodic energy components. This is because of the switching operation in a switching regulator. This may not be present in a feedback regulator structure. It will not be present here, but it will be present in a switching regulator structure. And this frequency can be very high. It can be in the order of 2 megahertz and so on. Okay, the switching regulator's frequency can be in the order of megahertz or tens of megahertz as well. So there, in that case, also you end up getting some high frequency energy on the supply. So these things, anything that is periodic in nature and unwanted, we call it as pulse. Anything that is unwanted and random in nature, we just call them as noise. So that's the fundamental difference between noise and spurs. Okay, a spur is an unwanted periodic component, and noise is a random component. So if you plot the power spectral density for a noise, it will be spread over a range of frequencies. Okay, so it will be a continuous spectrum. The power spectral density will be a continuous spectrum. So if I ask you what is the power, and if I ask you what is the power in a bandwidth, say delta F, so what you will normally do is you'll integrate it. So you'll integrate it in the range delta F. Sn of F is the power spectral density of noise, and find it out. And if your delta F vanishes to 0, then the value of this integral will tend to 0. That's the definition of a density function. Okay, a continuous density function. If you integrate it over a very narrow range, the power will keep decreasing, and eventually the power will go to 0. So that's what I said, that if you know the unwanted component is random noise, if I ask you what is the power at any specific frequency, it is 0. But power in a range of frequencies will be finite. Okay, so that's something to keep in mind. For a spur, on the other hand, if you plot the power spectral density of a spur, it will be just one impulse at a single frequency. Impulses are, in practice, you don't have an impulse function, but for mathematical convenience, we use impulse functions, because impulse functions are functions which can exist for no time, right? If I ask you to find out the spread of the impulse function, it is 0. But it will integrate out to a finite value. If I ask you what is the area of the integration, if you have some continuous function which is existing for no time, then the area of the integral will also be 0. But impulse is a very unique function. Even though its occupancy in time or frequency is 0, it will integrate out to a finite value. If I integrate this, you will get a finite value. So spur is represented in frequency domain using impulses. So that's the difference between spur and noise. Spurs will always be present in supplies. In PLLs, it will be present in the loop itself. Its operation generates spurs, unwanted components. So in my case, where I was designing this RC circuit, I had to filter out high frequency spurs. Now I'll come back to the problem. I'll finish this, then we can start with our discussion session. So your job is to filter out this unwanted noise and unwanted spurs. Okay. And your problem is you're limited on area. So capacitors cost area. If you want to put a large capacitor, it's going to cost you area. Okay. So you're limited on area. So therefore, you can't just keep increasing your capacitor value as much as you want. Now, the question that we had to, or at least I was trying to answer at that point, the value of R and C are fixed. Even resistors, when the value is very large, they also take up area, right? So semiconductor resistors are typically used, fabricated on chip, and they are usually you just dope some region using some specific impurities. Then you can control the resistance of those of that material. So that is, I mean, any standard textbook on semiconductor device physics will contain how resistors are fabricated. Capacitors, there are two different flavors of capacitors. One is called metal to MOM capacitors, metal on metal, or MIM, metal insulator metal capacitors. So that's like a parallel plate capacitor. And in between, there will be an insulator, which typically will be silicon dioxide in a CMOS process. Okay. And they end up costing a lot of area. So capacitors are also realized using MOSFETs. Even they also cost, they are slightly better than metal and metal capacitors. So you take your MOS structure, a MOSFET, and then short your drain and source, and you apply your gate voltage to be greater than the threshold voltage of the MOSFET, then the channel becomes conducting. When the channel becomes conducting, then it will behave like a parallel plate capacitor. Gate will be one plate, your channel will be another plate. Okay, so this is your channel, drain to source is your channel, that will behave like another plate. And the oxide between gate and metal, the gate and semiconductor, will act like the insulator between the two metal plates. So that is also another way of realizing capacitors. But the problem is that this, I mean, the advantage is that this will give you a better area density. You can compress a larger capacitor value in a smaller area when compared to metal and metal capacitors. Still, the problem is capacitors cost you area. So that's the problem. Now my goal is to reduce high frequency noise. So what I was looking at is R is fixed, C is fixed. I can't increase my R and C values. But if I want to filter out high frequency noise, is a single RC section good? Or can I cascade it and form two RC sections? I'll take the resistor, split it into two halves, split it into two fractions, say R1 and R2. The sum of R1 and R2 is R. And similarly, I'll take the capacitance and split it into two caps and call it C1 plus C2. The sum of the two caps is again C. That is also fixed. Now my question is, what kind of responses can I expect from these two structures? And if I want to filter out high frequency noise, which is better? That's what I was trying to answer. So for that, we'll just very quickly, I'll take you through some mathematics, and then, we will finally draw some conclusions from that. So a transfer function for a first order RC filter is very simple. It is simply 1 by 1 plus SRC. And how to derive transfer function for this is, I have videos in it, and it's a very trivial circuit. So it's 1 by 1 plus SRC. If you draw the frequency response, it will be, the frequency response will roll off after 1 by 2 pi RC in the hertz. F here is in hertz. After this frequency, the frequency will roll off. So that's why it's a low pass filter. At some high frequency of interest, I needed a certain rejection. Accordingly, I had already chosen the filter, RC cutoff. Now what happens? How does the frequency response of a cascaded RC structure will look like? That's what I'll try to answer. The second order circuit, it's a low pass circuit. There are no zeros in the circuit. So directly, I can say the transfer function will look something like this. And the DC gain for the circuit is 1, right? So if open circuit, both the capacitors, input and output are, the gain is 1. So you'll have 1 divided by transfer function should look something like this, of this form. 1 by 1 plus S into something and S square into something. Or you can simply see that this is a system with two capacitors, which means it will have two poles, no zeros. So the transfer function should look something like this: 1 by S plus omega P1 into 1 by S plus omega P2. And D gain is 1. So we don't have a problem. Okay. So this is the transfer function for this circuit. Fine. Now, if you see for this, in this circuit, I've just multiplied these S terms and then I get this expression here. I'm now trying to plot the frequency response of this graph. Where will be the poles and zeros? First of all, I haven't even found out what are the terms in S here, what is this term here, and also what is the term in S square here, right? So I'll try to find out those two terms. For a second order circuit, especially RC circuit like this, one simple way is just multiply all R's and C's and then just write it out. That will give you the S square coefficient. Okay, so that will be R1, R2, C1, C2. That will just give you the S square coefficient. The coefficient of S can be found by finding out the Elmore delay of the circuit. If you have taken any basic course on digital design, you know what Elmore delay is. So what we do is to find out Elmore delay, there are two capacitors in the circuit. So which means there are two time constants associated with the circuit. For each capacitor, you find out what is the time constant. So if I want to charge the first capacitor C1, then the charging path is through R1. So the time constant will be R1 C1. Then you add it with the second time constant, which is the time constant of the capacitor C2. So you remove the capacitor C1. So this technique is called open circuit time constants. I think I've discussed it in one of the videos, and you'll also find it in any standard textbook. You open C1 and keep C2 and find out what is the time constant now. Now it will be R1 plus R2 into C2. This is also called Elmore delay, or the overall time constant of this circuit. Okay, so that will form the coefficient of the S term. In fact, this holds true for a cascaded RC network. Even for an nth order circuit, you can just find out the Elmore delay and write out the second term. That's it. So now you have the transfer function. So you have the first term, second term, and the third term, all the three terms, and you have the transfer function ready. The next question is, how do I plot this transfer function? So when you are plotting transfer function, what exactly does that mean? You are just changing the frequency slowly and then seeing how the magnitude response changes as a function of frequency. So S equal to j omega, or j into 2 pi f here, the whole square. And I'll substitute S equal to j into 2 pi f. Now, as I'm increasing my frequency slowly, let's not worry about complex and real terms here. As I'm increasing my frequency slowly, this term is S square. And remember, let's say you have a function x and x square, say kx, and say some k1x and k2x square. Always, the k1x function will always increase faster initially. And then your k2x square function will start increasing. It will increase slowly initially because just find out the slope of the function. The slope of the function is k1 here. The slope of this function is k2 times x, 2 into k2 times x. And the slope of this function at 0, x equal to 0, is 0. So incrementally, if I'm changing my x here, the first guy will change fast. It will have a larger increment. So therefore, your linear ramp function will increase faster compared to a parabolic function. Then after a point, your parabolic function will overtake the ramp function. Okay, so that's a standard thing. We'll use that knowledge here. You have three terms here. The first term here is constant. I'm slowly increasing my frequency right now. So you should expect the second term to dominate first. So as I'm increasing my frequency and trying to plot the time constant, for the time being, I'll erase the the first order response. I'm only showing the second order response now. I'm increasing this slowly. As I increase this, what happens here is that you get a pole at 1 by 2 pi tau Elmore. Right? The second term has not kicked in yet. Second term has not kicked in yet. You have only the first two terms, right? So the transfer function will look something like this: 1 by 1 plus s into tau Elmore delay. And this, this is a first order system with a pole at 1 by 2 pi into tau Elmore. So 1 by 2 pi into tau Elmore is the pole. And after that, it starts rolling down with a first order response. After this frequency, you just equate 1 equal to s into tau Elmore. At that point, this term, the second term will become equal to 1. This term will become equal to 1. After that, this term will start becoming larger than 1, so you can ignore 1 after that. Then the transfer function will become 1 by s into tau Elmore. So that's what is shown. It will be a first order response. It will keep on decaying. And then the second term will start overtaking. Or the s square term will start increasing. As the s square term starts increasing, there will be a point when it will become equal to s tau 1. Right? It is increasing slowly as a function of frequency. At one point, it will become equal to this. That is the point where you get the second pole. Okay? So just equate those two terms and you can find out that, and that's what I've done here. I've equated this term here. Okay, s square R1, R2, C1, C2. If it's equal to s into tau Elmore, you get an expression for the second pole. The first pole, I said, is just 1 by tau Elmore. And the tau Elmore, I can just rearrange the terms and write it in this format. See, I've already given this condition. R1 plus R2 is R. C1 plus C2 is C. These are the two conditions that I've given. The Elmore delay is nothing but R1 C1 plus R1 plus R2 into C2. Just rearrange the terms. You can just go through this. I'll send you the slide. You can just go through that. Finally, you can express the Elmore delay in terms of R and C as RC minus R2C1, which means the Elmore delay is smaller than RC, right? I'm comparing this with the first order response. So the first order response looks something like this. So here, okay, the first order response will look something like this. It's time constant 1 by RC. Your tau is smaller, which means the pole will be, since your Elmore tau is smaller than the RC tau, right? So let me call this as tau Elmore, RC as tau, the time constant of the first order response, minus R2C1, which means the Elmore delay is smaller than RC or in RC product, which means 1 by that will be larger. So that's why in the second order RC circuit, the pole will occur after 1 by RC. Okay, the pole occurs after 1 by RC. For a first order system, it occurs at 1 by RC. The first pole itself will occur after RC, 1 by RC. The second pole will occur much later than 1 by RC. And the expression for the second pole, again, you can do some estimations here as well. This will turn out to be much greater than the Elmore pole as well. There is some, I mean, you can look at it intuitively as well, but let's know from mathematical point of view, you can just take it that it's going to occur at a much later frequency. Now, as an engineer, what is your goal? Your goal is, even if I'm putting the second order filter, R1C1, R2C2, your decision is to see if a second order filter is better than a first order filter. Keeping in mind, you have to keep the area same. The area of this filter and this filter should be exactly the same. They should not be different. You have to keep that in mind. Keeping that in mind, you have to answer a question. Can this give me better filtering at higher frequencies? Or the range of frequencies where I'm looking at, which one will give me a better filter? That's the call that you have to take. So that's why we are carrying out this analysis. Now, looking at this expression, you have to ask yourself a simple question. If it's a low pass filter you want, and you are using it to filter out noise and spurs, you want its poles to be as close to origin as possible, right? Which means you want to minimize this term. You want to, if you look at this term here, you want to minimize this term, right? The second pole, you want to keep it as close as possible. You want to minimize this term. Now, looking at this expression, I can say, if I want to minimize this term, I'll maximize my denominator, right? I have to minimize the overall term, so I'll have to maximize the denominator. If I want to maximize the second term, what is the condition? The condition is I have to maximize R1, R2, C1, C2 has to be maximized. Under the condition R1 plus R2, the sum of the two resistors is constant and sum of the two capacitors is constant. Okay, R1 plus R2 is constant, C1 plus C2 is also constant. This is the condition under which you have to optimize this. Now we'll assume that R and C values are fixed and they are independent of each other. We have chosen R and we have chosen C. We are not going to touch them, which means those two values are fixed. So this product is independent of each other. Maximize the overall product amounts to maximizing the individual terms. I have to maximize R1, R2 and maximize C1, C2. Now, this is a trivial problem. I mean, this problem is something that we encounter in information theory. You also encounter in probability and statistics. The problem is you want to maximize the product of two variables where the sum is given to be a constant. Okay. So then you can just plot it. It will look like this. R1, R2. I need to plot R1 into R2. And remember, the value of R1 and R2 cannot exceed R, right? The sum is equal to R. So which means individually their values cannot be exceed R and both of them are positive. It's given to that. That condition is given. So first I'll start sweeping R1 from 0 to R. And I'll try to plot this function R1 into R2. So this can be written as R1 into R minus R1. So it becomes a simple second order parabolic function. When R1 is 0, the product is 0. And when R1 is R, again the product is 0. As you keep increasing R1, it will behave like a parabolic function which means see, the function starts at 0 and ends at 0. And initially, it's increasing. And how is it increasing? You can just differentiate for small values of R1 and show that it's actually positive. Okay, its slope is positive. So which means it is increasing, which means somewhere it reaches a maximum value and then returns back to 0. That's what this tells me. Okay, and how do you find that maximum value? Use differentiate, just take this function, differentiate it with respect to R1 equal to 0. When you do that, you get R1 to be equal to R2 to be R by 2. Okay, so this is also something you get a similar problem even in what we call maximum power transfer theorem. Not exactly the same, slightly similar. So you get R1 and R2 to be equal to half of, or the average of the two values. So that's the answer here. I want to maximize the product of two variables where the sum is given to be constant. Then the values of the x1 and x2, which maximizes this, will be the average value of the two functions, two variables, x1 and x1 plus x2 by 2. So which will be k by 2 in this case. Okay, so that's something to keep in mind. Okay, just 1 minute. Yeah, so the value that maximizes this will be R by 2. Similarly, for the capacitor also, you can show the value that maximizes will be C by 2. So now I'll plug in R by 2, R1 and R2 as R by 2 and C by 2. Then the response will look something. The pole locations, the Elmore delay becomes 3 by 4 RC. So the pole will be 4 by 3 RC. The first pole will be 4 by 3 RC. The second pole occurs from this expression. You can take this expression and solve it. So if you substitute, you get RC minus RC by 4 divided by RC by 16. I mean, substitute each one as R by 2, R by 2, C by 2 and C by 2. You get RC by 16. And so the second pole, which you will get here will be, so this is actually RC minus will be 3 by 4 RC into 16. Okay. So that's 12 RC. So 1 by 12 RC. 12 by RC. Okay, I'm sorry. That will be 12 by RC. So this is RC square by 16. So what you get here is 12 by RC. And okay, I think I made some small calculation mistake here. So this should be 12 by RC. 12 by 2 pi RC. Okay, so this term is not RC by 2, it is 3 by 4 RC. So what you get is 1 by RC into 16 into 3 by 4. So 9 by RC. So this is actually 9 by RC. So the second pole occurs at 9 by 2 pi RC. Okay, so that's the overall response of this system. Now I have plotted both the responses together. If you take a single pole system, okay, if you take a single pole system, the yellow curve shows the single pole system. The two pole system, the first pole occurs slightly away from the single pole of a single or a simple RC circuit. Now I have R by 2, C by 2, R by 2, C by 2. By doing this, I get a second order response, yes, which is a good thing. But what happens is that the pole, the bandwidth increases, which means filtering decreases. And the first pole occurs at 4 by 3 times the pole of a first order system. The second pole comes only at 9 by 9 times this pole, the first pole. Okay, so let me call the first pole as omega p. Then the first pole of this guy is going to be at 4 by 3 times omega p. The second pole is approximately, again, these are all derived with approximations. Second pole will approximately occur at 9 times omega p. What I'm interested in is that if I have to compare these two filter responses, right? I want to know at what point the second order response will give me a better filtering than the first order response. I will find that out by equating the point where the second order response crosses the first order response. After the first pole, the first order response is going to be just 1 by SRC, right? I can just ignore 1 here. The transfer function for this guy is 1 by 1 plus SRC. At high frequencies, I can ignore 1. S is a frequency term. Similarly, at high frequencies for this capacitor, it's going to be 1 by S square into R1, R2, C1, C2. So that's going to be RC the whole square by 16. Now I have to equate those two. If I equate those two and then find out what is that, that term is going to be 16 by RC. So the second pole is going to arrive at, is it 12 by RC? Did I make any mistake? Oh, yeah, you're right. It's 12 by RC. I think one of you just pointed it out. It's 12 by RC. You're right. So it's 16 into, so 4 and 4, it will be 12 by RC. Yeah, you're right. So it's 12 by RC here. And the second pole will be at 12 times omega P. And the point where the crossover happens will be at 16 by RC. Okay. So now you have all this information. You have optimized to the best of your ability a second order system and arrived at the values of R and C's. Now the question is, by looking at these two responses, you have to say which is good for you. Remember, RC is fixed. You can't change RC. That is coming from an area specification. You don't have much of area on your chip. Area is limited. So you can't just keep increasing C. Now, between these two, which one will you pick? That's what you have to look at. Now, obviously, if you look at this graph, the green curve is good only after 16 by RC. After 16 by RC, if you see, right, the green curve is going to give me much better filtering. It will just diverge, right? So yellow curve is just going to go like this. So which means the filtering will keep diverging. The rejection that you can get out of this, okay? The rejection that you get out of the second order filter will just keep increasing like crazy. As you keep increasing higher and higher frequencies, going to higher frequencies, at the same frequency, you will get much higher rejection. Okay, so that's the advantage of going for second order. But the problem is you get all these benefits only after 16 by RC. Okay, so which means for more than a decade, your first pole had come at omega P. Until 16 times omega P, the first order response was giving me a better rejection because it is always lower. So whenever I say better rejection, it's lower than the second order response. Okay, it's lower in this entire region. Only after 16 times omega P, you start getting better rejection from a second order system. In my case, what happened was I was interested only in very high frequency spurs. So luckily, my spurs were coming at the given the RC values. Most of my spurs were in this region. So I went for a second order RC cascade. If your spur lies in this region, then you should go for a first order RC structure. Okay, let's say either it is spur or noise, you are interested in decreasing it in this region, then you have to go for a first order response. Okay, so that's it. This is something you have to keep in mind. So this was the problem I was designing. And I'm just trying to show you how you can apply some simple reasoning. Otherwise, it will just be putting an RC filter, right? You have to just rely on some simulations to look at which is optimal. But intuitively, you can guess for simpler systems. Now, why do I stop with 2? Can I keep extending it to third order structure, fourth order? Yes, you can do that. And when it becomes more complex, analytical reasoning will be a little difficult. Okay, so you have to rely on simulation softwares at that point. At that point, you'll have to sweep all the resistor values, capacitor values, and find out what is the optimum you get. Okay, from that swept value, you have to find out what is the optimum values of R's and C's. For a second order, it was very simple. I just made some approximations and derived them. And this is how the response looks. Okay, and I was interested in canceling spurs in this region. So I went for a second order structure. So if you want to cancel out higher frequencies first, an RC structure is going to be always better than a simple RC structure. Okay. And how many RCs cascades you need to add? That you can decide from simulations whether you get better rejection or not at those frequencies of interest. Okay. So that's it. So that's the interesting problem that I had in mind, which I wanted to discuss. I'll stop recording now, and then I'll open it up for discussion.